Okay, good morning, everyone. Welcome back. Please, I hope you can hear me. So this is our last meeting for the semester. I really appreciate all your hard work and your cooperation, right? I mean, the online thing is not an easy thing. Sometimes it feels like you're cut off, but you guys have done awesome. Yeah. So thank you for your cooperation. It's been nice working with you all, right? I sent you an email to wrap up what you're supposed to expect for the remaining of the semester, right? Once more, please, I make this announcement. If you've not done your evaluation, please make it a point to try and do it, right? To encourage you, I will award like some extra points on the final, right? So please make it a point to do it. And when you are done, just send me proof, right? Take a snapshot of where it says submitted, right? With my name there, and then I'll consider that. Okay, so thank you. Now, do you have any questions for me? Your final is on the 12th of May, right? And it's going to be from 7:30 to 7:30 a.m. to 9:30 a.m. Yeah. Please, any other questions? Okay. Well, feel free to let me know if any other questions come up. Well, I mean, about the general class, not necessarily about what I'm going to teach today, right? So if you have any other questions too, feel free to bring them up as we go, right? Okay, so now, without further questions, let's get on to today's session. Let me share my screen. Please, I'm sharing my screen now. If you can't see, do let me know. Oh, wait, no, not this one. I think it's right here, 5.5. You're supposed to see a PowerPoint slide, right? Okay, so on 5.5, you are wrapping up with the substitution rule, right? The substitution rule. So now, for this one, let me just try and explain why we need this, right? And then we'll get on to work on what is on the PowerPoint. So now I'm sharing the a whiteboard, right? A whiteboard. If you can't see, do let me know. So the thing is, when we start with this integration thing, right? Suppose we look at an indefinite integral. Say I give you indefinite integral, say secant squared of x dx. If I asked you to evaluate this integral, then what will you say this is? Well, you say, oh, it's just the antiderivative. So that'll be tangent of x plus c. Well, that's good. Okay. This is one of the functions. In this case, right, the integrand. This function here has a direct antiderivative. You can just get it, right, directly. You don't have to do any manipulation. You don't have to rewrite it in a different way, any other different way. As you see, the secant squared, the antiderivative is tangent of x. That's it. You're done. Well, on another case, right, you could be given something like, say, what do you call it? Let's say s plus 1 all squared dx. Now, for this one, if you are asked to evaluate this, well, you can't just say this one has a direct antiderivative, right? Because when you look at it, you say, oh, the square of s plus 1, is there any function that we differentiate to get that directly? No, we don't have any function that we differentiate to get that directly, right? So what we are going to say is, first, we can manipulate this, right? We can, let me do some stories on it so that we know there's a different point. Well, I'll say, okay, now let me simplify what is here a bit, right? So I'll do s plus 1 times itself, right? So that's s plus 1, s plus 1. So you get s squared plus 2s plus 1, right? And then dx. Well, looking at this structure here, you see that it's a sum of 3 terms. And for each of these terms, we can get the antiderivative. So the second point is where we have to manipulate the integrand, the integrand, right? We have to manipulate the integrand before we can get the antiderivative. So in this case, we get s cubed over 3 plus s squared plus x plus c, and then we have our answer. However, all that we've learned up to this point, right? We are able to obtain the antiderivative when it's direct, or we have to manipulate it and get it, right? But suppose someone asks you to get an antiderivative for something like this, say s plus 1 to the power, say 1000 dx. Then the question is, how am I going to do this? There's no direct antiderivative for this. And I won't even think about trying to expand this and doing it 10 by 10. Because like that's like to a power 1000. right? Can you imagine all the work that you have to do for that, right? Maybe you probably get like about 1,000 terms that you have to get it. No, that's too much work. Okay, so in such a case, let's look at one single case where we can actually get the antiderivative, where we cannot simplify the integrand, right? Now, to do that, I want to draw your attention to the chain rule, right? Let's draw attention to the chain rule. Now, we said for the chain rule, if you're trying to differentiate a composite function, you have the outer function and some inner function, right? Then, when you differentiate, what do you get? You get what? Differentiate the outer function, plug in the inner function, times what? The derivative of the inner function. That's the chain rule. So, in cases where the integrand cannot be simplified, if we can see the integrand to be such that it is a composite function, right? So what I mean by that is you look at the function, the integrand, and then it takes this form where you see that, oh, there is some inner function, which when you differentiate can give you the structure of the outer function, right? So look at just the integrand, right? Look at the integrand. And then think about the outer function of the whole integrand. Think about if you can decompose it into some composite function, which has like the inner function, you can differentiate and get some outer function. If that's the case, then you can say, oh, then I'm going to use something we call the substitution rule. So it's all about reversing the chain rule, right? It's about reversing the chain rule, right? So now let me just show you something here, right? Or let me show you something here, and then you talk more about it on the PowerPoint. So for this one, what we are saying is for this function that it appears you are stuck. Let's look at how you can use the substitution rule to do it. So for this function, I'll say, okay, maybe I can look at this as a composite function where I have x plus 1, right? X plus 1 is my inner function. Now for this x plus 1, if I differentiate it, I'm going to get 1, which matches what? This outer. I mean, 1 wasn't there, I just brought it there. But for any number, you can just write it as that number times 1, right? So that means that this integrand here matches this. It's like some inner function which we can differentiate to get an outer function, which is part of what? The integrand. So in that case, I'll say, okay, if that's the case, then I'll say, let u be that inner function. So in this case, the inner function that I'm looking at here is s plus 1, right? Immediately you let u be the s plus 1, then what you're going to do is get the differential of u. So du will be equal to what? Du will be equal to what? Dx, right? So now, this procedure that we're doing is called a substitution rule because we make this substitution. We let u be that s plus 1, right? That's why it gets its name, the substitution rule from, right? So let u be equal to that inner function and then get the differential. Now, what you're going to end up doing is we are going to rewrite the whole integral. We are going to change it from x to u. You're going to change it from an independent variable of x to an independent variable of u. That's the goal, right? So when I make this substitution and get this differential, right, I'll say, okay, now let me try and rewrite this whole thing in terms of u, no longer x, right, in terms of u. So I come here, the integral sign is still there. For this s plus 1, I'm going to replace it with what? With u. So I go u to the what? 1,000. And then for this one, I see dx can also, ds has to be replaced, right? Because when you have dx, it means that the independent variable is x, right? But since you're changing the variable to u, we need the independent variable to be u. But we've already seen that dx is just du. So we can replace this dx also by what? Du. And now, for this function, for this integral that we have, you see that we can get the antiderivative. See? Because u to the 1,000, if you want to get the antiderivative, you just do what? The power rule. So you just do 1,000 plus 1 over the result, 1,000 plus 1, and then plus c, right? But this u wasn't what the question asked us in. The question asked us for the integration of what? With the variable x. U is something we introduced, right? So in the long run, after getting your result in terms of u, you must bring back the x variable in there, right? So we are up to this point. Please, any questions on the explanation so far? I'll do another example on the PowerPoint. so that you get this point. But I'm trying to explain how you get it here, at least. Yeah. Anybody needs time here? Okay. So then moving on, everything simplifies to what? U to the 1001 over 1001 plus C. But U is equal to what? S plus 1, right? That was a substitution we made up here. So that means that our final answer is going to be what? S plus 1 to the 1001 over 10001 plus C. And that's what? Our indefinite integral. So that's how you go about the process. Please, any questions here? Okay. Anybody needs time here? Okay. Then let me get back to the PowerPoint. Yeah. So for this one, this is saying that our anti-differentiation formulas, they don't tell us how to evaluate integrals like this, because for this one, we start, okay, do you have a direct antiderivative for 2x square root of 1 plus s squared dx? No, nothing comes to mind. Like for 2x square root of 1 plus s squared, no, we don't have a direct antiderivative. Okay, so can we manipulate this and simplify? No, you can't multiply it out. This is like 2x times, is 2s and then times 1 plus s squared all squared and to the half, sorry. So you can't multiply it out to get it term by term and get the antiderivative. So it's okay. Then we move on to the next step, which is the substitution rule. Do we have some composite function, some inner function, which we can see as a composition, such that when we differentiate it, we get the outer function? Well, for this one, I see, oh, 1 plus s squared is underneath a square root. And then for this 1 plus s squared, a quick differentiation of 1 plus s squared will give me 2x. And that exactly matches what is outside here. Now, talking about matching what is surrounding that composite function, please, constants are not really important, because for constants, we can just create and destroy them. Like we can just bring in a constant, right? For example, if the 2 wasn't here, right? If 2 wasn't here, I can just create 2 and also multiply by half, which will still give me, like, it will cancel up. So I can create the 2. I can bring the constant there, but I can't bring a variable there. I can't just introduce a variable. For a constant, I can introduce a constant at any point in time. So even if I had something like square root of s times 1 square root of 1 plus s squared dx, then I'll say, okay, is there some inner function which I'll differentiate for it to match the surrounding function? If I look at this, right, I say, okay, 1 plus s squared is a candidate. Now, if I differentiate 1 plus s squared, I'm getting 2x, right? But it's 2x. Now, the focus won't be on the 2. It will rather be on the fact that it's x to the power 1, and that matches this. Because for 2, I can create 2 and multiply by half. Nothing has changed. It's still 2x. So when you're doing this process, constants can be created. So when you're thinking of the matching thing, just think about matching in terms of the structure, like the power, the degree, right? Or something around that line, but not necessarily the constants. Okay. So when we are able to identify that expression, which will differentiate to get the surrounding function, right? Then we let u be equal to that. Immediately you let u be equal to that, the rest is just going to be like cut and dry, like everything follows. So the main difficulty or the main challenge is trying to identify what your u is. When you figure out the u, everything will follow. It's always the same procedure, right? Now, as you move on, maybe in Calc 2, you learn much more advanced stuff. Yeah, you learn modification to this. But for now, yeah, we are here, right? So let me show you how we're going to do this. So let me go back to the whiteboard. So this example, no, this one didn't give any example. So let's say question on PowerPoint slide. Let me just say slides. Okay, so for this one, I have this 2x square root of what? 1 plus s squared dx. So I ran through the processes. This one, do you have a direct antiderivative for this? No, I don't. Okay. Can I manipulate this? Maybe multiply it out so that I get it term by term and then get the antiderivative for each? No, I can't. Okay, then I should be thinking about the substitution rule. Can I see this to be some inner function whose derivative give me the surrounding outer function? Well, for 1 plus s squared, if I differentiate it, I get 2x, and that matches this. Perfect. So that means I'll say let u be equal to what? 1 plus s squared, right? So that's the main challenge. Immediately you find your u, the goal is to try and what? Use substitution to rewrite the variable from x to u, right? From x to u. So in that case, I'll need a representation for the x. I need to change all these x stuff into u. Okay, so now let's proceed. With the u equal to 1 plus s squared, I need to find the u, right? So I'll get the differential du. So the u will be equal to, so just differentiate this. I hope you remember this from 3.10, section 3.10, differentials. So you get du will be equal to what? So differentiate this with respect to x. The derivative of 1 is 0. The derivative of x squared is 2x. So I get 2x and then dx, right? Okay. Now, the thing is, we are trying to make a substitution here, all right? A u substitution. So now let's look at the differential and then the u substitution we have and rewrite this integral in terms of u. So I say, okay, now I have 2x dx. 2x dx is du. That means I can replace this 2x dx with u. And then for this 1 plus s squared, I can replace that with what? With u. So that's where it gets its name, substitution. Right, so I'm going to have elongated s. 2x dx is what? Is du. I'll just write my du here. And then the square root of 1 plus s squared is what? It's just square root of what? What is 1 plus s squared? Is u. So u. So now I have what? Integral of what? U to the half du. Now this one is simplified. I can now get this one. Immediately you make the substitution, right? You can get the what? The antiderivative. So then at this point, I'll say, okay, now add 1 to the power, divide by the result, right? And then plus c, right? So now what do I have? Half plus 1 is 3 over 2. So that one can be rewritten as 2 over 3, right? And then I have u to the 3 over 2 and then plus c, right? Okay. Now, for this one, u is something we introduced, right? And then we know that u is what? 1 plus s squared. We know u is 1 plus s squared, right? So for this one, substituting in the back in terms of x, I have 2 over 3, and then 1 plus s squared to the 3 over 2, and then plus c. Please, are you okay with this? Any questions? Anybody has any issues with this? Give me a sec. There's an issue here. Okay, issue resolved. Yeah, please, any questions here? Anybody needs time? Is there any part you want me to explain again? Okay. So the main thing is u. Immediately you find your u, everything follows. Same way. Okay, then let me go back to the PowerPoint. Okay, so this is just illustrating what I just talked about, right? So we let u be equal to this. How do we set the u? We try and find some inner functions whose derivative will match the surrounding expression, the surrounding remaining expression, right? So we let u be equal to 1 plus s squared because the derivative of 1 plus s squared is 2x, which matches this. And then everything will follow from there, right? And then when you're done, please don't forget to put back your u substitution back in. And then you have it in terms of x. Okay. Now, the thing is, whenever you get your result, right, don't forget you can always differentiate to see if you get the integrand, right? And then the thing is, for this answer that we had, for 2 over 3, 1 plus s squared, all to the 3 over 2 plus c, when you differentiate this, you are going to have what? That 2x square root of 1 plus s squared, which is exactly the same as what? This integrand. So that's how you verify that your answer is right. Please, are you okay with this? Any questions here? Okay. So as I explained, right, this is from chain rule. So if you have an integral with the elongated s here, and then the uppercase f prime of j of s and j prime of s, you see that this inner functions here derivative matches what is outside it, what is surrounding it, right? So that means that we have what? This, right? The composite function plus c, right? So this is what I explained earlier on the whiteboard, that this one is related to what? The chain rule, right? It's just a chain rule reversed. Yeah. So now this is a formal definition, right? So the substitution rule. So if u equal to g of x is a differentiable function whose range is an interval I and f is continuous on I, then f of g of s times g prime of s dx is just f of u du, right? So we are letting u be equal to what? This inner function g of s, whose derivative will match what is outside here, right? Okay. Please, any questions so far? Anybody needs time here? Is there any part you don't understand? We'll be doing more examples from here. Okay. Now, this one is just drawing our attention that we have to remember that these are differentials, right? Yeah, and always these differentials have to follow the integral signs, right? They are always there, like here or there, to illustrate that the x or the u is the independent variable which you are integrating with respect to. So that's their function. So you always must have that in mind, that you don't leave your differential dx if you are making a substitution. The u has to be there because the u shows that the independent variable is u, not x, right? So you have to substitute everything, including the differential. Yeah, that's the point this is saying. Okay, so now let's look at this example. So for this one, before we start, can anyone please tell me what you think the u should be? What do you think the u should be? That's the main thing. If you figure that one out, you can do the rest. So please tell me what the u should be, and then we do. I think the solution is here, right? Yeah, the solution is here. So we work it on a whiteboard. But before we start, what do you think the u should be here? Anybody? Okay, so I have 4SQ. Close, very close. I think you have an idea, right? You have the idea, you're close. S cube, still close. SQ cosine, close. I like the input. Please try your best, let's see who gets it. What should you be? Now, the hint is you're looking for a function which looks like some inner function, which we can differentiate to get some structure surrounding or with the remaining parts of the integrand, like some function structure which surrounds the integrand, which is part of the integrand. There is a function, when you differentiate it, it's like an inner function which we've plugged into something. But when you differentiate it, you get the degree to match what is outside, or the structure to match what is outside. What is surrounding what is in the integrand? Anybody? Okay. So perfect. Thank you. Yeah. So it's s to the power 4 plus 2 is this. Why? What are the properties? This one is some inner function because you are plugging it into cosine. Okay. Then the derivative of this quickly will tell you that it's 4s cubed, right? And then the s cubed part matches, as I told you, the constant don't matter, right? The s cubed part matches this s cubed, which is part of the integrand, but wasn't used as our substitution, right? So that means that that is precisely what our u should be. Please, are you okay with that? Yeah. So you get better with more practice. Okay, so now let's go. I'm looking at example 1 on slides. Okay, so now we have integral s cubed cosine of what? S to the power 4 plus 2 dx. So the thing is, we are saying let u be equal to what? S to the power 4 plus 2. Immediately we get our u, let's get the differential. So we have the u equal to what? 4s cubed dx. Okay. Now, for this one, unlike the previous cases where the structure directly matched what is here, right? For this one, we have 4 attached to it. So to make the substitution, we just need s cubed dx. We don't need 4s cubed dx. Right? We don't need 4s cubed dx. We don't need a 4. So what can we do? Well, in such a case, you say, oh, it's a matter of just dividing both sides by 4. Right? So we get s cubed dx to be equal to the u over 4. That's why constant don't really matter, right? Because when we have the constant not part of it, we can just divide it by both sides and still get that structure, right? So the main goal is to get a structure, like the variable and then the differential, not like the constant. Okay, so now we are here. Right, so we have s cubed dx to be equal to this. Now that we have it, we can make the substitution from x to what? To u. So I'll bring my elongated s. Now I know s cubed dx is what? Du over 4. Differentials are always at the end, right? So that's why I write the differential thing at the very end. And then I have cosine of what? What is s to the power 4 plus 2? It's u. So now I have this, right? Now, remember that du over 4 is the same as 1 over 4 times du, right? So please note this. If you see du over 4 is the same as 1 over 4 times du, right? Okay, so for this one, I can say, okay, let me perhaps bring the constant out, right? Remember that by the properties of integrals, when you have a constant in there, you can pull it out. So I'll pull out the 1 over 4, so that I'm left with what? 1 over 4 integral of what? Cosine of what? U du. So everything reduces to getting the antiderivative of what? Of cosine of u. What's the antiderivative of cosine of u? Well, the antiderivative of cosine of u is what? Is sine of u, right? So I have 1 over 4 waiting outside, and then sine of u, and then plus c. But what is u? U is something we changed, right? We brought it in. But the question is in x, right? So we look at the substitution here again, and then say, oh, u is what? S to the power 4 plus 2, and put it in. Right? So we have 1 over 4 sine of what? S to the power 4 plus 2, and then plus c. Now, finally, we have our result. Please, are you okay here? Any questions? Is there any part you want me to explain again? Or you are fine? Okay. Anybody needs time here? Okay. Okay, then let's go back. So this will just show us like the solution and a bit of explanations to this. Right, so that's what you see here. And then you get this. So this one says, notice that at the final stage, we had to return to the original variable, right? That's very important. Okay. Any questions here? Okay. Now, we've learned how to do it for indefinite integrals. Now, the question is, how do you use the substitution rule for definite integrals? That's when there are limits of integration and we expect the answer to be a constant. So how do you do it? Now, for this, there are two approaches. So I'm going to show you the two, right? So we are going to, question is this, right? So let me go to the whiteboard and then look at that one for definite integrals under substitution rule. Okay, so now the question is, there's 0 to 4, and then square root of 2x plus 1 dx. Okay, so for this, how do you do it? Well, I'm going to show you two approaches, as I said. Approach 1. For the first approach, remember that this integral, right, this definite integral is the same as what? Is the same as finding the indefinite integral, right? And then evaluating for at the limits of integration. Just find the indefinite integral and evaluate at the upper and the lower limits of integration. That's all. So that means if we look at it in this sense, then all that we have to do is first get this 2s plus 1 dx. First get this indefinite integral. And when you're done, plug in the upper limit minus plug in the lower limit. That's all, right? So for this one, we look at this and try and run through the integration processes, right? So the first thing, do we have a direct antiderivative for this? No, we don't. Can we manipulate this so that it's term by term and you can get the antiderivative of each term? No, we can't. Okay, next thing, substitution rule. Can we make a substitution so that the derivative of that inner function will match what is outside? Well, for here, if I let u be, can anyone tell me what u is? Please help me and let's see if you can practice and get this one. Anybody? Okay, I have someone. Perfect. It's 2s plus 1. Perfect. Right? So in this case, the 2s plus 1 is some inner function. It's under a square root, right? And then the derivative of 2s plus 1 is 2. But don't worry about the constant 2. All that is saying is it's a constant. And outside, I can create a constant because there's no x variable surrounding it. It's just a constant 1. So that is perfect. So u equal to 2s plus 1. Nice. So immediately I set my u. That's the main challenge. Get the differential and then make the substitution. So I go, okay, what is the u? U be equal to what? Derivative of 2x is what? Is 2. Derivative of 1 is 0. But don't forget, it's a differential. So multiply by dx. But the thing is, looking at what is surrounding it, I have dx here, not 2dx. So I can just solve for dx as what? Du over 2. Or half times du. Okay, now I'm ready to make my substitution. So I go, okay, this integral is now going to become, bring the elongated s. Now square root of 2s plus 1 is now square root of u. And then dx is now what? Du over 2. I can pull out the constant 1 over 2. And then I have integral u to the half and then du. Now, when I get this, I can get the antiderivative, right? It's just half plus 1 over half plus 1. And then I have half here. And then plus c. Right? Don't forget, this one is an indefinite integral for now. Okay, so now for this one, the 2 times 3 over 2 down here will reduce everything to 1 over 3. And then the u to the half plus 1 is 3 over 2. So you have something like this, and then plus c. But please don't forget to bring back your, change the variable back to the original, right? So we do 1 over 3. What is u? It's 2x plus 1 to the 3 over 2, and then plus c. But we are not done. This one is what? It's a definite integral. So we have to evaluate at the upper limit and then minus what? Evaluated at the lower limit, right? So that means that we have this 0 to 4 square root of 2x plus 1 dx to be equal to what? So it's just going to be, since you are doing definite integral, at this point you can ignore the c. So it's just going to be 1 over 3, 2s plus 1 to the 3 over 2, and then all evaluated from 0 to 4. Even if you bring the c's will cancel out, right? For definite integrals, we don't really bother about the c. So you are here. Please, any questions so far? I hope you're okay. Is there any part you don't understand that you want me to go over? Okay, so then moving on, we have, so plug in the upper limit, right? So 4. So that'll be 1 over 3. 1 over 3, and then 2 times 4 plus 1. All to the power what? 3 over 2. 3 over 2. And then, yeah, I put it in right. Yeah, that's 4. And then close. And then minus what? 1 over 3. So plug in 0. That'll be 2 times 0 plus 1. All to the 3 over 2. I hope that's correct. Yeah, that's correct. Right? And then you just evaluate, right? So for this one, 2 times 4 is 8. 8 plus 1 is 9. 9 to the 3 over 2 is 27. And then 27 divided by 3 is 9. So I have 9 for this side. Now for this side, I have 2 times 0 is 0, and then 0 plus 1 is 1. 1 to the 3 over 2 is 1. So I have 1 times 3, 1 over 3, which is 1 over 3. Right? So in the long run, I have what? 26 over 3. Because this 27 over 3 minus 1. Yeah, minus 1 over 3, which is 26 over 3. And that's my answer. Please, are you okay with this? Yeah. Well, let me erase this so that someone will not say it's 2.6. Yeah, 26. Now, let me show you the second approach. Now, I prefer the second approach, but it's good to know the two because sometimes it's best to use one of them than the other, right? So approach 2. The second approach is simple, quite simple. Okay, so now for the second approach, you're still having this question, right? So 0 to 4, definite integral 0 to 4 square root of 2s plus 1 dx. And then we agree that we let u be equal to what? 2s plus 1. Now for the second approach, immediately you set your u, right? You will change the limits of integration to based on the u substitution that you do. So what I mean by this is, whenever we have this definite integral, right, and the independent variable is x, what it's telling us is the limit of integration is s equal to 0 down here, right? And then s equal to 4 up here. That's what it means. Even though we don't write the x there because you know that if the independent variable is here, then your limits of integration are showing you the points of the independent variable. So we don't write the variables there, right? So this is s0, s4, right? Okay. Now we want to change these limits of integration also into some limits of integration for u. So how do you do it? Well, it's based on the substitution that you made here, right? You said u equal to 2s plus 1. So when u equal to 2s plus 1, then that means that when x is equal to 4, u will be equal to what? 2 times 4 plus 1. And that's equal to 2 times 4 is 8. 8 plus 1 is 9. And then when x is equal to 0, that means your u will be equal to what? 2 times 0 plus 1. And that is what? It's 1. So now, when you are making the substitution, you will change the limits of integration as well as the integrand and then the differential. And you change everything in terms of u. So you get a new definite integral. And for that one, you don't have to return to any original variable. You can work with that, right? And get your answer. Okay, so now let's go. Please, any questions on this? Okay, so now we are here, right? So we have u equal to what? 2x plus 1. So you get a differential, like the usual stuff, right? So the u will be equal to what? 2 dx. And you say, oh, I don't have 2 dx surrounding it, right? I don't have 2 dx surrounding this composite function. I just have dx. So I'll solve for dx to be equal to the du over 2, just like how we did it in the previous case. The only addition is you are changing the limits of integration as well, right? That's the only addition. Okay, so now that we have the differential dx also with a solution, we can substitute everything, right? So for this approach, we know that when x is 0, the u is supposed to be what? Supposed to be 1. So we have a new lower limit of what? Integration. When x is equal to 0, u is 1. And then for the upper limit, when s is 4, u is what? It's 9. So write it there, right? And the square root of 2s plus 1 will be what? Square root of what? The 2s plus 1 is u, so square root of u, right? And then we have what? Dx. Dx is what? Du over 2. Du over 2. Now, for this one, as I said, you don't need to return to any original variable. Immediately you have this definite integral, it's like you can take your mind off the original question that you were given. This will give you the answer that you want, right? So right here, we just forget about all the x stuff. Focus on this definite integral. The answer to this is what? Is our answer to the problem. Okay. So for this one, we have 1 to the 1 to 9, u to the half. And then I can pull out the half here from this du over 2. Don't forget the u over 2 is the same as the u times half, or half times the u. So pull out the half, and then I have the u here. Now I can get the what? Antiderivative for u to the half. It's just u to the half plus 1 over half plus 1. And then times 1 over 2. And then for this one, since I'm obtaining a definite integral, immediately I get this result. I just do from 1 to 9, right? Okay, please, any questions so far? And then at this point, I say, okay, now I have half, and then this one is 3 over 2. So that the 2 times 3 over 2 is 1 over 3. So 1 over 3, and then u to the 3 over 2. And then I'm integrating from 1 to 9, like so, right? So I just need to plug in the upper limit minus plug in the lower limit, right? Like we always do. But I'll need to do that on the next slide. Please do let me know if you need more time here. Okay, so that means we are getting, plug in the 9. So that'll be 1 over 3. Where is 9? 9 to the 3 over 2. 9 to the 3 over 2 for the first part. And then minus 1 over 3, plug in the what? What's the other one? The other limit is 1. So 1 to the 3 over 2. Okay, so now let's try and simplify everything. For 9 to the 3 over 2, that's just going to be 27, right? So I have 27 over 3, which is the same as 9. And then minus 1 to the 3 over 2 is 1. 1 times 1 over 3 is 1 over 3. So 27 over 3 minus 1 over 3, that's 26 over 3. You see, that's the same answer that we had when we did it the other way. So now it's up to you, right? Which one you prefer. But as you move on, when you move on to 182, it will be best to know the two approaches, because sometimes using one will help, right, than the other, because you may be doing it like several steps. Definitely integral, you make several substitutions, like about 3 levels, right? So sometimes it's good to alternate between them, the two approaches. But for this class, you just need one of them, right? Yeah, please, any questions here? Is there any part you need me to explain further? Okay. Then anybody needs time on this slide? Okay, then let's go to the PowerPoint and see if we have some more questions or if that's it. Yeah, so that's what it's showing us, right? There's a solution. So here, let me see, which approach did they use? it used the first approach, right? It got the indefinite integral and then evaluated at the same limits of integration, right? So that was the first approach that I did. And then there's the definition, right? So this is saying, this definition actually shows the second approach. It says, if J prime is continuous on a closed interval and F is continuous on the range of U equal to G of S, then if you have this representation of the integrand, then you can make a U substitution, but you have to also change the limits of integration, right? Don't forget that the substitution is U equal to G of X. So if you are changing the limits of integration, when X is B, U will become what? G of B. And when X is A, U will become what? G of A. That's why you see these limits of integration there. And then F of U du. So you get a new definite integral. And unlike the indefinite integral, for this one, you can ignore the previous definite integral you had in terms of X. You can just work with this because you don't return to any original variable. This same integral will give you your answer, and that's all. So this slide is going to show us the second approach, like this one, the one I showed you, approach 2, right? So you change the limits of integration as well. You see 1 and 9, and then you get a new integral, right? And then you just do it, and then you get this same answer. Okay. Any questions? So that's what they're saying. Remember that we do not return to any original variable, right? Using the second method. Any questions? Any comments? Any part you need me to explain again? Okay. Now, the last piece is symmetry, right? So sometimes when you're integrating stuff, it's not always that straightforward. Sometimes you can use some shortcuts to help you get to your answer, right? So now let's talk about symmetry. Now in chapter 4.7, when we're doing curve sketching, I introduced these 2 points, that a function can be symmetric to the origin, right? In which case it's an odd function, or it can be what? Symmetric to the y-axis, in which case it's an even function. Well, it turns out that if you have a function f, which is continuous on some closed interval, and then the endpoints of the interval are just additive inverses. So we have negative a to a, right? Say for example, for negative 1 to 1 or negative 2 to 2, they have to be additive inverses. So this has to be true, right? Now, the thing is, if f is an even function, so if the integrand is an even function, and you're integrating from what? Say negative a to a, then your result, you can actually cut your work short by doing what? Twice integrate from what? 0 to a, f of s dx. On the other hand, if f is an odd function, if the integrand is an odd function, and you're integrating from negative a to a, then your definite integral is just 0. Now, I'm not going to prove this, but a graph will illustrate this point, right? So let's look at these 2 cases. Now, for the first case, we know that if a function is an even function and is symmetric to the y-axis, then from 0 to a is like a reflection in the x-axis to get from 0 to negative infinity, right? As you approach, no, in this case, not negative infinity, to negative a, right? So 0 to a is the same as what? From 0 to negative a, right? So recall that the definite integral can sometimes be interpreted as the area under a curve if it's strictly positive. So if you have the integrand to be positive here, then this is the definite integral, right? So if you are finding the definite integral over this entire region, then it's just this area will be the same as that area. So that's why we say just find the area from 0 to a and do it twice, 2 times that, right? So it makes sense geometrically. Now, a very, very nice one to know is the one where your result is 0, because for this one, you don't even have to do any integration. You don't have to find antiderivatives, right? So suppose you have an odd function, right? So from negative a to a, for the odd function is symmetric about the origin. So there will be from 0 to a will be, say, a positive side. Well, it could be on this side from 0 to negative a. But the fact is, one will be on the positive side and the other one will be on the negative side. And because the areas are the same, this one is a positive area, that is a negative area. So they will cancel out when you take the definite integral. So that will give you 0. And this really helps, right? This is really helpful. if you have a very messed up or complicated integrand, and then you're able to identify that it's an odd function, then your work is really easy, right? As long as you are integrating from negative a to a, you can just say your answer is 0. That's all. You don't need to show anything. Just say that the integrand is an odd function, and then we have the range of integration to be from negative a to a. If that's the case, your answer is 0. You're done. Okay. Please, I hope this makes sense. Any questions here? Okay. So, yeah, they're just talking about what I just explained, right? Because the areas cancel, that's for odd function case, right? Yeah. Okay, so now let's apply these. So I'm going to go to the whiteboard to solve this, right? So example 10. Okay, so for this one, I have an integral from -2, from -2 to 2, and then s to the 6 plus 1, and then dx. Okay, I know we can use the usual approach, just get the antiderivative and plug it in and so on. But one thing you realize is when you plug in 0, it usually goes to 0. That's one motivation why people will use this even function property. So we start with this, and I say, okay, I can do it directly. I mean, I can get an antiderivative plugin, but I want to show you this even function thing, right? So what I say is, okay, this integrand here, because I have an integral from what? An additive inverse to is from a number to its additive inverse, from -2 to 2. I will say, okay, what kind of function is here? Is the integrand. Well, for the integrand, if I plug in -x, I have -x to the power 6 plus 1, which is the same as s to the power 6 plus 1, which is the original function. So that means that this is what? An even function. Now, because this is an even function, I know that, oh, for even function, if I'm integrating from a number to its additive inverse, then the definite integral of this will just be equal to twice, and then integrate from 0 to 2, s to the 6 plus 1, and then dx. So let me just focus on this integral 0 to 2, s to the 6 plus 1, dx, right? And this will be easier, a bit easier, because I'll be plugging in 0 for one of them, right? For when I'm evaluating the limits of integration. So this gives me s to the 7 over 7 plus x, and then integrate from 0 to 2, right? So I plug in 2, I get 2 to the 7 over 7 plus 2. And then when I plug in 0, I get 0 to the 7 over 7 plus 0. So 2 over 2, 2 to the power 7, and then this was the answer. Let me see. The rest is just calculated. 284 over 7. 284 over 7. Wow, let me see. No, it won't be 2 over 4, because this one is, so 284 divided by 4, that's 2. That's 142. 284. Yeah, this 142 over 7. Then I say, okay, so that means that the integral from -2 to 2 of s to the power 6 plus 1, it will be twice this area. So it will be 2 times what? 142 over 7. Right, so that's 284 over 7. Please, I hope this makes sense. Any questions? Now, to my favorite, the odd function one. That is my favorite. So now let's go to that one. That is my favorite, right? My favorite amongst these properties. So that one is example 11. So for that one, they give you this integral. They say, oh, -1 to 1 tan of x over 1 plus s squared all to the s to the power 4 dx. So I say, oh, this integrand looks really, really strange. How am I even going to find the antiderivative here? It's ridiculous. But then I say, oh, this is additive, a number and its additive inverse, -1 to 1. Oh, let me investigate. Right. So for this function, f of x equal to tan of x over 1 plus s squared plus s to the power 4. Okay, let me plug in -x and see. It will be tan of what? -x. 1 plus negative s squared plus negative s to the power 4. Tan of negative s is negative tan of x over what? 1 plus s squared plus s to the power 4. Oh, it's the negative of the function. Oh, this is an odd function. Nice. Immediately I realized that it's an odd function. Integral is 0. I'm done. That's all. Okay. So that's the end. It's exactly 11:50. Thank you so much, as I said, for all your effort. Please don't forget to submit your evaluations and send me proof. Right. And that's all for this session. And preparing towards the exam, feel free to reach out if you don't understand anything. If you want to solve more examples, I'll be holding office hours. You can send me a link. You can send me an email. I'll send you a link. You can schedule a meeting or something. Yeah, so all the best. Enjoy the rest of your day and have a good finals and everything. See you another time. You guys are welcome. Yes, there's a discussion session tomorrow. Yeah. I think that'll be your last meeting because Wednesday is prep day. Yeah. You're welcome, Timothy.